Again, page 15. Yep, page 15. Number 7, it says find the derivative of each using limit definition and or properties of exponential and log functions. All right, so we could try to do this with the limit definition. I can tell you that it's not going to get us anywhere. All right, that's one of those things, like in the past, I would show you that it would not get us anywhere, just to say, okay, well, now that we tried that, let's try something else. Let's just kind of believe me when I say that applying the limit definition is it's not going to get us anywhere. All right, so we're going to try a different approach. All right, and this different approach has more to do with our knowledge of logarithms than it does, or exponential functions and logs, than it does with our knowledge of derivatives, which is interesting. So I'm going to rewrite this as y equals ln of x. All right, very small change. So instead of f of x, y equals, that's pretty easy. All right. Now, we don't know how to take the derivative of a log, which is, why we're here. We're in this predicament. But I do know how to take the derivative of an exponential function. All right. Now, we learned or reviewed, that finding an exponential function from a logarithm isn't really that bad. All right. It's just a matter of making a conversion. All right. So that log, that ln of x, can be thought of as log base e of x. All right. Now, again, what a log is telling us or asking us is what power would I have to raise the base to, this jammy here, in order to get this as a result, this x as a result. So what power must e be raised to in order to equal x? All right, so it's going to be e raised to some power giving a result of x. All right, we reviewed yesterday that power is the result of the logarithm. That's the whole point. All right, so that would be y. So e to the y is equal to x. Now there's shortcuts for this. You probably, if you remember anything from last year related to logs, it was probably converting from one form to the other. All right, so if you have something like, for example, log base b of e, actually I think it's, the acronym is, it's BEN, so b n e is equal to b to the e equals n. Yeah, this is the conversion. It's a little shortcut, a little mnemonic that some people use to convert from one form to the other. All right. You might have, I don't know if you've heard the logger Dan has DNA. You might be familiar. Depending on the teacher that you had previously, you heard different mnemonics. But basically, it's the idea that you can get from log form to exponential form without going through the exact definition of a logarithm. Really what's happening is you start off with the common base, because the base of the log and the base of the exponential are always going to be the same. If you're in log form, it's pretty easy because you could just work your way around in that circular pattern, and that'll tell you the ordering of values from left to right. So it would be b to the e power, b raised to the e, is equal to n. All right. So the b for base, e for exponent, and n for some number. All right. So for example, if I had log base 2 of 3 is equal to x, I would say that that's equivalent to 2 to the x is equal to 3. All right, so then the only thing you're really thinking about is which form is more advantageous? All right, the log form or the exponential form? All right, for this example that I just came up with off the top of my head, it turns out that the log form is more advantageous because you can just pop that right into the calculator. Log base 2 of 3, get an answer. This one, not so much because it has a variable trapped in an exponent. All right, but that's just a quick example. Bottom line is, as long as you can convert back and forth between logs and exponentials, you're going to be in pretty good shape. All right, and so that's what happened here. If I actually just took, and I'll write it side by side, if I took log base e of x is equal to y, write it so that it's structured the same way as the rule. The bases will be the same. So I got a base e, and then I would just work my way around with that little circular motion here. E to the y is equal to x. All right, so that's another way that you can think about doing it. But the bottom line is, I wanted to represent my equation in a different form. The reason I wanted to do that is because I couldn't find the derivative in the form I was originally presented. I needed to change things up somehow. All right. So this is the same as x is equal to e to the y. All right. It's an equation that's solved for x in terms of y. All right. Normally, when I find a derivative, it's related to an equation that's solved for y in terms of x. All right. Solve for y in terms of x, we would get dy over dx as a derivative. All right. So I'll just kind of jot that. Well, I'll jot it down on the big screen. So if you were getting a derivative of a y function, so y in terms of x would correspond to a dy over dx. If you're taking the derivative of something that's solved for x in terms of y, it would get reversed. Your derivative would be the derivative of x with respect to y. I don't know, maybe this will help a little. The bottom of the screen is always going to be the problem, but at least I can make it a little bit bigger. So what I'm looking for here is the derivative of x in terms of y. All right, everything's reversed. It's an inverse. What do you do when you want to find an inverse? You flip the x with the y and solve for y. That would be the same idea here, essentially. But every instance of x gets swapped with every instance of y. So why would it be any different for a dy over dx? So I would just need to figure out what the derivative of e to the y is. Well, we have a rule. The derivative with respect to x of e to some function of x would be equal to e to that function of x times the derivative of that function of x. All right, so it's reliant on prior knowledge, but that prior knowledge is 2 pages ago in your packet, so it should be still there somewhere. So you rewrite your exponential and then take the derivative of that exponential. But then it's like, all right, well, this isn't in terms of x, it's in terms of y. So what do? I'll change all my x's to y's. It's going to be the same process. So d dy of some exponential function where the variable is a function of y is going to be e to the f of y times f prime of y. I think we need those risers. You know, like the bed risers. You need like those for the desks and chairs, or just like the stadium approach, where everything's like on an incline. Like I mean, I love technology, but like the screen is so tiny, and to mount it so low, it it doesn't always end up being an issue because most of my classes aren't this big. But here we are, size wise and also like age wise. So we get taller folk in here. You know, the little freshmen, different story. You know, they can see over each other pretty easily. I'm just trying to remember. Well, anyway, I'll remind you where the saved notes are, because all of this, everything I write down here gets saved. I tried doing it so that people could follow the live document online, but there's a little bit of a lag. But if you ever miss anything, you probably get it that way. All right. So anyway, long story short, the derivative of e to the y is just going to be e to the y. Nope, that's not a marker. All right, because the derivative of an exponential e is going to be itself. Since I'm taking the derivative in terms of y, I'm just really treating this as if it were e to the x. All right, I'm just changing my mindset. All right, so I would say if this were e to the x, what would its derivative be? E to the x. All right, it's e to the y. So what would its derivative be? Because we're changing, y is taking on the role of x. So every aspect of y would take on every aspect of x, and therefore its derivative would be e to the y instead of e to the x. All right, but ultimately I need dy over dx, because if I go back to what we started with here, I have to find the derivative of this equation here. Y is equal to the natural log of x. That derivative is going to be dy over dx is equal to something. All right. Well, I have dx over dy. I don't have dy over dx, but it's a proportion. All right. So that e to the y, I could write that as e to the y over 1. If you have a proportion, you can flip both sides of that proportion to save yourself from having to cross multiply or any kind of reciprocal stuff. Flip both sides simultaneously, you get dy over dx is equal to 1 over e to the y. So we have a derivative, it's just not in terms of x. Fortunately, I have a relationship here between x and e to the y. It says right here that x and e to the y are the same thing. That allows a substitution. And that in turn tells me that the derivative dy over dx, the derivative of my original function, instead of saying 1 over e to the y, I could just say 1 over x. All right. But we run into a little bit of an issue, and the issue isn't computing the derivative. It more so has to do with the domain considerations, because a natural log function only exists for positive values of x. Right? Can't take log of 0, can't take log of negative number. So we'd also have to state that this is only true. That's supposed to be a semicolon. They always end up looking like J's. I apologize. But only true for when x is greater than 0. All right? And that's because the domain of y equals ln of x is x is greater than 0. All right? The domain of the original function restricts the domain of the derivative, right? Because the derivative, I mean, it's very easy to lose sight of what we're talking about. The derivative is the slope of the tangent line at any point along the curve, all right? Any point along the curve. So it kind of follows that the curve has to exist in order to have a slope, right? So if there's a part of the original curve that does not exist, then why would we account for that in its derivative? All right. So let me just pop this up on Desmos and show you the bits and pieces here. All right. So we have y equals, well, I'll actually do f of x. E equals ln of x. All right, you see the natural log function only exists to the right of the y-axis. But then if I put in my derivative function, just y equals 1 over x, I get a whole lot more graph than I bargained for. All right, as opposed to having the calculator, having Desmos compute the derivative for me, f prime of x, it only shows one part of that. All right, and that would be the part that's to the right of the y-axis, the part that corresponds to the domain of the original function. All right, so that's telling me that I have more in the blue graph than I really need. But if I throw in a little domain restriction here, x greater than 0, now I have only the part that I care about. All right. Or at least really the only part that's relevant to the derivative. All right. So what we get from this, at long last, is a very simple rule. Oh, okay, that's weird. Oh, because I didn't do split screen. That's why. We get a simple rule, and that is that the derivative of the natural log of x is just 1 over x, but specifically where x is greater than 0. All right. So I'm going to put this down at the bottom. So the derivative with respect to x of ln of x is equal to 1 over x where x is greater than 0. All right. But we also just learned, indirectly, but we also just kind of pulled from this whole experience that we could do the same thing in terms of y for a function defined in terms of y. And that its derivative would be 1 over y. But again, with a similar restriction, y would have to be greater than 0. All right. Some pretty advanced looking notation right there. It's like smart looking math. That's the kind when you're on the train or the plane, you're going back to your college classes after like Thanksgiving break or something, and you're just banging out some math homework and you're jotting this down. Person looking over your shoulder is like, wow. That's some pretty smart looking stuff right there, I always enjoyed those moments because I always had this thought, especially when I was doing science work. I'm looking around. I'm like, you all are so impressed by what I'm writing down on paper. What you don't know is I have no idea what any of it means. But I look so smart writing it. So this is good. Right. So anyway, number 8. Actually, numbers 8 and 9 are super easy now because we have properties of logs that are going to help us do all of the hard work, and we have a nice, easy derivative rule that's going to take care of the calculus for us. Now, coming up with that nice, easy derivative rule was not nice and easy, but now that we have the rule, we don't need to reinvent the wheel. All right. So natural log of 4. Remember, the power rule for logarithms tells us that we could take that exponent of 4 and hop it over to log. ln of x to the 4th power is the same as 4 times ln of x. We also know, because we've been doing derivatives now for a little bit. If we have a coefficient, that doesn't factor into the derivative process. All right, we hang on to a coefficient. When finding the derivative, we leave that coefficient alone and take the derivative separately of that parent function. All right, so this would be the same as saying 4 times just the derivative of the natural log of x. And this is an intermediate step, the green stuff that I wrote here, that you wouldn't have to write. I'm just doing it for note-taking purposes, or just so you understand where the next step is coming from. But the derivative with respect to x of the natural log of x, we now know is 1 over x multiplied by that constant multiple of 4 would give us a 4 over x. All right? So constant multiples, that 4 is a constant multiple. You leave that alone and take the derivative around it. All right? So we differentiate around constant multiples. All right, so we applied one log rule and one basic derivative rule, and that was it. That's not bad. I mean, compared to the one that we did before it. I mean, the one before it was actually even easier, except we derived like derivation, as in discovering the rule. We figured out the rule from prior knowledge. You know, that took a little doing, but now that we know the rule, we can rely on it, and it's not too bad. Like the next one looks a little bit more intimidating, but we have a power rule for logarithms, but we also have a product rule. All right, we actually want to take care of the product rule first. So looking at this, I see I have a 5 times x to the third power. Now that x to the third, that power of 3 does not apply to the 5, it only applies to the x. So I need to split up this logarithm before I can apply any kind of power rule. So I would say ln of 5 plus ln of x to the third. All right. Then I could apply my power rule for logarithms. Swing that exponent down, make it a coefficient, and I'd be looking at ln of 5 plus 3 times ln of x. That's my f of x. All right. So we've manipulated the expression to make it more convenient. We put it as a simpler logarithm so that it's easy to find the derivative. All right. Now, I can tell you it happens all the time on every test that I've ever given related to this topic, no matter what the course is. High school, college, different levels of calculus, whatever, AP, and it doesn't make a difference. There's always a student or two that'll stop in this step and be like, yep, feel like I did a pretty good job here. Looking good. Because they feel like they did a fair amount of work, and they feel like the mission accomplished. I've done all the work I needed to do. Never actually found the derivative. So they did the part where they cleaned it up and made it nice and easy to find the derivative, but never actually found the derivative. And because of that, it's like, how much credit can I give you? You didn't do the calculus. All right, so just be careful about that. But I'm looking at this and I'm seeing a constant. Now this is not a constant multiple, this is just a constant. Being able to identify these things are hugely important, or is hugely important, because a constant, by definition, is something that is not changing. Something that is not changing would have a rate of change equal to 0. Since the derivative represents the rate of change, the derivative would be equal to 0. Right? 3 times the natural log of x, we just talked about this. The 3 is a constant multiple. All right, so this is a constant multiple. different from a constant. All right? It's a multiplier to a parent function that can be differentiated. So what we do is we just hang on to that. So we just bring it along for the ride, kind of like a GCF. You know, when you factor out a GCF, you still got to factor other things, but you always bring the GCF along for the ride. Think of this as the GCF for a derivative problem. All right? Now, the derivative with respect to x of the natural log of x, that's equal to just a 1 over x. So this, at long last, f prime of x, is going to just become a 3 over x. All right, so as long as you know that a constant goes to 0, when you differentiate, you're going to be in pretty good shape, because that was probably the only scary part about this. Now, a big question that usually comes along the lines, because when you're dealing with logs and exponentials and other transcendentals like trig functions and stuff like that, oftentimes you'll come across something that is constant, but you won't recognize it for being constant. Just think to yourself, if there's no variable in it, it's constant. All right, it doesn't matter how complicated it looks. If there's no variable in the expression, it's constant. ln of 5 is constant because there's no x there. All right, and the relevant variable in this function is x. All right, you look at L and N and you say, oh, those are letters, but they're not variables. All right, they're just functions. All right, so I can even show you an example. ln of 5. Desmos is saying the derivative of that is equal to 0. All right, but if I say ln of 5x, it's saying that the derivative is something else. All right, it's not 0. All right, but I could even do something like the sine of the natural log of 5 squared. You know, something funky looking. Bottom line is, I didn't put a variable in there. So its derivative is going to be 0. There's no variable, so its derivative, no matter how complicated it looks, the derivative is going to be equal to 0. Yeah. If there's no variable. So then we get to this juicy one right here, number 10. That doesn't have an ln in it, but we can make it so that it does. All right. So first thing I would want to do is apply my log rules and simplify it as much as possible, because maybe it'll clean up nicely, but maybe it won't. We'll see. All right. So we're looking at a quotient here, a ratio of two terms. So I'll apply my quotient rule, log base 2 of x cubed minus log base 2 of 2. I could also apply my power rule for logs. Three log base 2 of x minus log base 2 of 2. Now, you may recognize log base 2 of 2 as being something that could be simplified, because again, we go back to what the definition of a logarithm is. All right, so we talk about the base and ask ourselves, what power would that base have to be raised to in order to get the argument of the logarithm, the subject of the log? In this case, 2 to the first power would give us a 2. So the result of this log would be equal to equal to a 1. All right. But a nice little rule is if the base and the argument in the logarithm are equal, then it simplifies to a 1. All right. However, you don't really need to know that, because when we differentiate, again, just going back to what we talked about with something that's constant, there's no variable in there. It's going to 0 anyway. All right. So my function here, yeah, it's got a variable in part of it, but this part of it, regardless of how it simplifies in the original function, it's still constant because there's no variable. So when I differentiate, that part's going to 0 and therefore is irrelevant. All right, so the only part I actually care about is this. Now I look at this and I say, well, I don't know how to find the derivative of a log with a base 2. But then I kind of think back and I say, well, wait a minute, but I do know how to find the derivative of a natural log. And there is a change of base formula. We can convert from log base anything to log base anything else. All right. What we want to do exclusively is convert from log base something other than e to log base e. All right. So let's say you have log base b of a. That's going to be equivalent to the natural log of a over the natural log of b. All right. So it's always the natural log of whatever the subject of the log is. That gives you the top. And then the natural log of whatever the base of the log is. That gives you the bottom. All right. Can make it a little bit nicer. All right. By writing it as, and it's not going to seem like it's nicer, but it almost always is. We could write this as 1 over ln b times ln a. All right, so what I have here, bless you. Yeah, he gets his money's worth. You kind of have no choice but to pay attention in this class. Because if that sneeze catches you off guard, you might have a heart attack. So anyway, log base 2 of x, the a is being replaced with an x, and the b is getting replaced with a 2. So this can be thought of as natural log of x over natural log of 2, or 1 over ln 2 times ln of x. So I'm going to replace the log base 2 of x with 1 over ln of 2 times ln of x. We can clean it up a smidge, not a whole heck of a lot, but this would become 3 over ln of 2 ln of x minus log base 2 of 2. And now we're in a position where we could actually find the log, the derivative of this log equation or log expression. All right, because this part is constant, no variable whatsoever, and this part is a constant multiple. All right, the constant multiple just comes along for the ride, just like a GCF. The derivative of the natural log of x is 1 over x, and a constant goes to 0. So we actually have our answer, f prime of x is going to be 3 over x ln 2. All right. But just like the other problems we talked about, there is a domain consideration. X has to be greater than 0. And that's actually true for the other problems, that even the ones I didn't write. I might have forgot to write it, but we do have to account for the fact that x has to be greater than 0, because we'll get a lot of graph that's irrelevant if we just assume that it's 3 over x ln 2. All right. Now, if we kind of think about what happened here, we'll actually get to another rule. All right. So if I kind of look at this a piece at a time, you see we got the 1 over x. That part came from the log component. But then everything else sort of came from the coefficients in some capacity. You know, so if you look at our final answer, we have a 3 in there and we have a 2 in there. All right? And if you look at the original problem here, I know it was a while ago. Well, not the original, but this one right here. It was 3 log base 2 of x. All right, so let me write them side by side. F of x, 3 log base 2 of x. All right, so that was my original function. My derivative I'm actually going to write it in the unsimplified form, 3 over ln of 2 times ln of x. If you look at it closely, you get to a little bit of a shortcut here because it looks like that base 2 has been accounted for in this denominator. It looks like that coefficient just came along for the ride and everything else amounted to the natural log, right? So if I wanted to take the derivative of some log equation or log expression with a base b of x, I would just be looking at 1 over the natural log of whatever the base is times the natural log of x. And the same would be true for y's. Just with those domain considerations. All right. So the whole point of this unit, I mean, even though it seems like it's designed to just torture you, it's really more to discover rules that we could then rely on moving forward, but at least understand the underlying concepts.